Hello, and I have honor to introduce our next speaker, Professor Margus Pedaste, who is my good colleague, and we know each other, I think that more than 20 years since I started my master's. Margus Pedaste is Professor of Education and Technology and the head of the Institute of Education at the University of Tartu. And he is a member of Committee of Education, Estonian Academy of Sciences. In addition, his prominent researcher's career, he has a long experience in teaching biology at school. He has led and participating in several national and international projects. His research focuses on improving learners' digital literacy, inquiry skills, and problem-solving abilities in the context of science education. Today, Margus will talk about meaningful use of technology to achieve science competencies based on DigiEffect project. So, Margus, the floor is yours.
Thank you, Monica. I didn't know that you are already 20 years old. Really? But we know each other for 20 years, and even more, maybe. Who knows? So thank you all for coming, and it's a pleasure to have some discussion with you on different topics related to science education and connecting science education with learning in digital environments. And many thanks to Mia, who invited me to this event and gave me the possibility to give this presentation. The presentation was titled Meaningful Use of Technology, and this is very important for me because when we started from this topic, then we realized that according to some international studies, technology might be not so useful as it was considered sometimes by students and teachers as well. Actually, we departed from the moment where 2018 PISA results showed that if you use technology, then your results are worse in math, science, and languages, which is quite common understanding, but it's not completely true, as I can say now based on our study. And I will go into this a bit more. So we designed a study, thanks to Estonian Ministry of Education and Research for funding this project. We had more than 30 people involved in this project, so thanks to all of them as well. And in this context, we focused on Estonian sample of students from the 3rd, 6th, and 9th grade. They were studying different subjects, science, Estonian language, and mathematics were in our focus. But in this presentation, I will focus only on data related to science learning. So we had almost 1,000 students from 14 different schools, and we focused on very wide range of different outcomes. And we can call them dependent and independent variables in our study. Which means that we were focusing on academic results, but also on digital competence, social-emotional skills, learning competence, agency. A lot of data is available from this project, and I will come back to that at the end of the presentation, because one of my aims here is also to show to you that actually everything what we have produced is available for you as well. That is the moment when I go back to the first slide, showing that already there, you see that we have a link here, bit.ly/SciCar Pedaste, which is the link that brings you to the presentation so that you can have everything from there as well. So, and in this study, we were also interested in this how much the variance in the students' outcomes depends on the student-level data and class-level data. So that what is what is actually coming from the teacher's side and what the teachers or classmates could have in means of impact. And we had quite general questions. The first one, how students learn. Second one, how teachers teach. Third one, how does it affect outcomes? If the learning process and teaching process has some effect on different types of learning outcomes, and how much of this variance could be predicted on different levels, student level and teacher level. So the design of the study was like this on this slide. Again, maybe you do not see from the back, so that then you can open your computers or smartphones, and on this slide you will see it on your own. But shortly, what I want to express here, that we had observations and interviews with teachers in the classrooms in Estonian schools. We had a collection of digital traces of their learning process, so that the students used electronic learning materials. In Estonia, we have that kind of e-book system like Opiq, that is the most widely used e-book in Estonian context. And we collected log files from those environments. But we also had different tests and questionnaires to collect information before the learning started and at the end of the learning process. We are focusing on the whole study year. We started somewhere in November and then finished somewhere in May and June with our data collection. And it was 2 years ago when COVID was more or less over, but there were still some moments when we had some breaks in schools, so that students had to be at home in this moment when they're learning. And we also collected data from teachers so that we will understand how the students and teachers' characteristics will have effect on students' learning outcomes. The title of the presentation was how meaningful use of technology could affect science competence, which means that we have to first define how do we understand what science competence is. And again, I should say that we always have limitations in this context, what we can measure. In this study, we focused on science competence through that kind of five areas: analytical skills, interpretation skills, planning skills, but not only skills, but also knowledge, subject knowledge, and, as we call it, inquiry knowledge. So you already see that this is all somehow linked to the inquiry process. But always content and subject knowledge is related to this inquiry process, so that they are combined. And what is missing probably here, if you think about the full picture of science competence, we didn't focus on attitudes related to science or science identity, different concepts like this. But in short, we departed really from the inquiry-oriented science process and tried to understand what are the important skills that could be differentiated in the learning process, so that we can support development of those skills, but we can also measure the outcomes. And in this context, we started from the inquiry cycle, what we have learned somewhere. And then we started from that actually students should be able to formulate questions or hypotheses. They should be able to collect additional information to formulate hypotheses. They should be able to plan studies and analyze the results and so on. But at the end, we found that actually the evaluation model doesn't support that kind of structuring of science competence dimensions. And that's why we ended up with a different model based on exploratory factor analysis. And this is now visible here. We used in this study hierarchical analysis, hierarchical modeling, to find what is the different effect of student and class level data in our case. And in this case, we also used some limitations, like we were focusing on science teachers, but we excluded those teachers who doesn't have enough students. We considered only those teachers who had at least 10 students in their class in our data set, which means that some of the students didn't respond as well. So the 5 scientific competence dimensions were used as dependent variables in our study. And first we looked at the intra-class correlation of those dependent variables. We wanted to understand how much of the variance in those 5 variables mentioned on the previous slide are actually described by the differences in the classes, so that it doesn't depend on the students, the diversity of the students, but it depends on the diversity of the classes. And it turned out that planning, for example, is the skill that doesn't depend so much on the student's ability or potential of learning about planning, but it depends at a very high level on the teacher's work, what teachers are doing, or how a learning process is organized in the classroom, so that actually peers will also have effect on the class level learning outcomes. But of course, we saw that there are some other areas, like interpretation and especially subject knowledge related topics, where we do not see so much differences in Estonian classrooms. So that we can conclude from that actually our teachers are quite equal in this, how they can teach knowledge. But it's much more difficult for them to teach scientific inquiry. So that's one message what we had. And then while we saw that kind of big or high-level inter-class correlations, we actually moved on towards understanding what makes that difference. What are the independent factors having effect on the outcomes? In this case, or in case of science competence. And we applied 3 models. 3 models with different difficulty levels, because in our study the main question was how technology might have effect, or technology use might have effect on the learning outcomes. Then we first looked at the model, the simplest one, where we used different descriptors of the learning process as the independent variables. And then the second model, a bit more complex model, where we used also that kind of information as independent variables as teachers' digital attitudes towards use of digital technologies, or students' digital competence, or how often students use digital devices in their learning process or in other activities. And the third model is a very complex model. In every model we had some 50 independent variables, which means that it's quite challenging to get significant effects in this model, where we took into account also background information that was available and that was not related directly to digital learning. Some messages from our data. First, we clustered what is happening in the classrooms. And this figure shows what kind of lesson profiles we will see in Estonian classrooms based on observations and interviews. And in the end, we saw that it's very much described based on G and Wiley's ICAP framework, which differentiates these different types of learning: interactive learning, constructive learning, active learning, passive learning. And we saw that there is quite a large number of lessons that we observed where actually the learning process is mostly passive when technology is in use. And this brings us back to the first question I had: why PISA results show that technology doesn't have effect. And the message might be, this is not yet this analysis, but it comes, the question might be that if so many teachers use technology passively, as I do it right now, The most engaging activities are least used, in this case interactive ones, then maybe the question is not if technology has been used, but how it has been used. And this is actually what is seen in our data later as well. The other idea what we got from the analysis of log files using Estonian ebooks was that actually the students' own learning process might be not enough guided by the teachers. So that we saw that often, and this is now a comparison of the 3rd, 6th and 9th grade, we saw that often it is so that students would like to focus on non-obligatory tests. We called them improvers. They really wanted to learn again and test themselves, how they progress in the learning process. But what we see when the time goes on, then in the 9th grade, a big number of students do not want to learn, but they want to complete their studies. So that they only do the formal tests, what are expected in the ebooks, if the teacher asks them to do so. So it might show that actually students are not really self-regulated learners, and they need to be guided by the teachers in order to learn effectively with technology. And if this has been not done, then we cannot expect that technology use has positive effect on learning outcomes. For example, to have effect on science competence. So we also had many other variables, just to list them here at the student level. How often students use computers, what is their cognitive ability, personality, anxiety, satisfaction, socioeconomic level of the family, special educational needs, gender, age, so that if you are interested in analyzing this data, you're welcome to do so. All the data is available. And we also had several class-level variables mainly related to teachers. What are science teachers' attitudes? What is teachers' digital readiness? Teachers' agency in different contexts, using IT, but also in planning their own learning and teaching process. And teachers' background, like career level and highest educational degree, age, and so on. And 2 more slides. Effects on science competence tests. In this case, student level. And here you see that we have several variables that have positive effect on science competence. But we also have variables that have negative effect. And in case of the green color, I can say that this was always positively linked to the science competence. So that we can say that if the students use computers and tablets or tablets for studying in the classroom, then it always has positive effect on science learning outcomes in this context. But in contrast, if they use smartphones for studying, which was a surprise, then it had negative effect on learning outcomes. Maybe those are too small for learning science, I don't know. Or we just do not have the proper learning strategies for using them effectively. And in case of the green ones, red ones, it is clear that this has been always negatively associated with the outcomes in this case. In case of black ones, of course, it is so that it depends on the science competence areas. We had 5 different dimensions. In some cases, it might have positive. In some other cases, negative effect. Again, a lot of ideas for thinking about what should be behind of those ideas. And what is very important for us in this digital competence is definitely needed in order to learn effectively using digital materials. And maybe we can go on with that knowledge. As you see at the class level, there are many more variables having positive effect on the learning outcomes, on science competence in this case, and many less on the negative side. And what is here? Maybe I could start from the negative side, actually. Teachers' agency in planning and teaching and learning. How I could interpret it. We have probably very experienced teachers who are really experts in teaching as they did 20 years ago. If they have so good experience and they are so good experts in this, then they might be better than using the new methods that should be first studied by themselves in order to gain proficiency. So that's why it might be so that if the teachers are very good in planning and teaching in the old ways, then it might have so that it might have negative effect on the learning outcomes actually. So what is positive? From the different profiles of the lessons, we saw that constructive activities are those that always lead to success. So that if the technology is used constructively, and to link it to previous presentations and discussions as well, which means that we have to first start from understanding students' knowledge, what they already know. We have to elicit this knowledge in order to move on. And then we have to construct the new knowledge, taking into account the existing knowledge the students have. So, and in this case, it was really having positive effect on science competence, and not only in case of science competence, in case of other dependent variables we studied in our study as well. Then the other variable that plays a very important role here, teachers' digital readiness, so that the teachers should be those who are capable for effective and meaningful use of technologies, so that they should understand how technology should be used or could be used constructively. And if this is not the case, then the results might be as they were according to the PISA study 2018. Then teachers' self-efficacy in engaging learners and applying different teaching strategies. Again, linked to that more or less. Teachers' experience, teachers' plans to carry on teaching. So those are different variables that could be taken into account in designing effective learning process to achieve science competence. And as I promised, I'm a believer of open research, and that's why I said that our presentation is available for everyone, but also our data collection instruments. 15 plus of them are available for everybody, and data collection instruments are unfortunately in Estonian. Some of them might be in English as well if you contact the authors of them, but all the data is available both in Estonian and English. So that a year ago I was at Marshall Lynch's group at Berkeley University, and the students at Berkeley already used this data in their coursework, for example. So that I'm happy if you use it, because the data is for reusing to avoid unnecessary data collection, so that we can focus on doing research without collecting new data from the sustainability point of view. And of course, our research outputs, about 20 different articles are available from our Estonian research portal. Thank you.
Thank you, Margus. And now we have a couple of minutes for questions or comments before a short break. So please use the time for asking questions.
So you would predict that if I had random sample over here, random sample over here, they all have the same learning goals, they all have the same technology, they all have the same instructional materials, right? So both randomly sampled groups, same learning goals, same technology, same instructional materials. The only difference is the instructional strategies. This group, passive, this group, constructive. Results would be?
In case of constructive learners, it should be better because of the ingredient. Yes.
Technology, right? That seems like the powerful impact is actually the task that the kids actually have to, it's actually how they have to carry out the task. If it's presented in a passive manner, it doesn't matter.
Yeah, that might be, that was not in the focus of our study, because our question was derived from the idea that actually why technology doesn't have effect. And the message might be that this technology itself is not an important player here, but actually the task is, as you said, constructive approach in using technology is better. Yeah.
Right, so let's add a third group just to see what you say. So we've got the passive group, we've got the constructive group with the technology. Now we have a constructive group, but without the technology.
I don't know. We didn't have that kind of analysis in our data set, but yeah. That's a new study to discover.
Thank you.
So one more question, Barbara?
Yes. And of course, because I didn't know what Joe was going to ask, my question was very similar. It's about the counterfactuals. So what are the counterfactuals that would possibly change your results? And I think that it's really important to think about, one, how it might have been without. I was thinking exactly the same thing if they didn't have a digital thing. And also, I was worried about the question about the students themselves and how much they're online and how good they are with all of this. So the result on the smartphone, I thought was really, of course that's a situation. If they're on their phones all the time to use them other than something other than studying, then basically, of course, you're going to get a negative effect on digitization if it's in the positive. So we've been on kind of a path where we've been two things, well, actually three things, because we do hierarchical linear modeling, we do all these things, and so the first is, what did we forget? So what's our problem in terms of the counterfactual that we didn't explore? In the case of, well, did we look at any schools or any situation where you didn't have digital technology? Number two, we also worry about how big is our effect. Because if it's significant and there's an effect, well, how big is it really? And how big, that depends on your power estimate, and that depends on a number of other factors, so that including what your likely sample size should be for the differences that you find. And the third thing, which I wanted to press you on, are these questions about confirmatory factor analysis, because it looks to me as if you've got a number of things that bunch together that could be basically into a confirmatory factor, that you don't need all of this, because it seems that your models are over you know, there's just too much in them to ferret out what would be the essence of what you find. And I just want you to know, for Joe and for myself, there's no way I would ever even think about not introducing technology into a class in science, especially today. And I have a meeting hopefully very soon with the US Department of Commerce to beg them to bring broadband and technology into the classroom, into places that don't have it. Because not today. Every single solitary student has to have access to Wi-Fi, has to be involved in some kind of digitization, because how can you live very soon where you won't have any cash, you won't have anything that you're not using technology for. So I want you to understand my issues are the typical kinds of things that someone who's in measurement and quantitative methods always asks. But from the standpoint, I'm with you 100% of the way. There's no way I could possibly think about doing this without something that was digital.
Yeah, first, of course, there was a lot of data, and we cannot go in depth with all of this. But what is maybe important in this case, if you have that kind of very complex models, in this case, I think that it is important to see that actually some of the traditionally important variables will fade out. Like, for example, cognitive ability didn't have any effect in our complex models on students' learning outcomes, which is quite surprising, actually. But one more comment I wanted to make is that, by surprise maybe for you, is that, for example, in Sweden, the politicians, educational politicians, are currently very actively discussing abandoning any technology use in schools.
Well, then they're having a problem.
Yeah, and that is...
I can't tell
yeah.
Where are you going to go with your
Yeah.
that are involved in technology in the future?
Exactly, yeah. And that's the problem. And where does it come? From that kind of studies, like PISA, for example, showing that technology is not good, if to simplify.
But I would like to stress, I mean, I've walked into lots of classrooms and where I thought it was going to be exciting to visit because they had technology. They were using some technology that I thought was extremely excellent. But the way it was introduced and the way the kids used it, the way the teachers introduced it, the way the kids, it was just as deadly as any lecture, right? So, I mean, it's not, the technology in itself isn't going to make a difference. It's how it's actually used that makes a difference. Right, but I think we always have to say that. It's just not the technology can be deadly. It's how we make use of it is what's going to make a difference. If we make use of it in a constructivist fashion, that's why I posed the question I did, then it makes a big difference. But if I could have a classroom that has lots of technology and a teacher that's not too good versus a classroom that has no technology and a great teacher, boy, this class wins all the time.
So thank you. We will run out of the time, so you can ask questions from Margus privately. So now we will have a 5 minutes break before panel discussion, and thank you for Margus.